Hello everyone, this is Pavni Pandey,
And this is Akriti Saxena.
and we enthusiastically welcome you all to the 8th episode of the Roundtable Society's podcast, TRT Unspoken. Listen, think, and analyze.
In the boundless expanse of the cosmos, we are but voyagers on a celestial vessel called Earth, adrift on an endless journey, daring to seek what lies beyond. Today, we're honored to sit down with one of the most pioneering minds in astrophysics, Professor Avi Loeb. A world-renowned theoretical physicist, Professor Loeb has reshaped how we think about our universe, pushing the boundaries of cosmic understanding.
The only thing more powerful than curiosity is a curious mind that refuses to take no for an answer. This sentiment perfectly encapsulates the work of Professor Avi Loeb. From his groundbreaking research on black holes and gravitational waves to his provocative theories on extraterrestrial life, Professor Loeb has published hundreds of influential papers. His recent insights delve into the mysteries of black holes, dark matter, and the fundamental nature of gravity, solidifying his reputation as a trailblazer in the field and an inspiring figure for all the aspiring scientists everywhere.
Highlighting today's topic, we will be diving deep into the fabric of space and time and unravel the enigmas of black holes, those cosmic giants that teach us humility and curiosity in equal measure. Let's begin this journey into the cosmos with Professor Avilo. Welcome, sir, to our podcast.
Thanks for having me. It's a great pleasure. I always enjoy speaking with young people.
The
The
pleasure is all
pleasure is
ours.
all ours.
So, as we all know, your career has been dedicated to unraveling the mysteries surrounding black holes, gravitational waves, and the nature of relativity. Could you please throw some light upon what initially sparked your interest about the fabric of space and time?
Yeah, so traditionally, historically, space and time were thought to be rigid, that you can't really change them. And what Einstein came up with is an insight. He realized that following Galileo, that all objects fall the same way under the influence of gravity. And that gave him a hint that perhaps, since it's universal, all objects go the same way, that it's a proper gravity is a property of space-time. And he formulated it as a curvature of space-time. And one way to think about it is, the Earth moves around the sun and it goes in nearly a circle. And if you were to imagine a trampoline that has a rubber surface, and you put a heavy object like a bowling ball at the center, it will curve the rubber, the surface of the trampoline. And if you were to put a marble and give it a kick with the right speed, it will go in a circle around the center. And then if you were to remove the bowling ball, the rubber will come back to be flat. And then the same marble will move on a straight line. So the same is true about Earth moving around the sun. It tries to go on a straight line, but in fact, because of the curvature of space-time, it's moving in a circle. And if you were to remove the sun, then the Earth will fly out on a straight line. So Einstein's insight was that gravity is nothing but the curvature of space and time. And of course, that has a lot of implications. For example, if you take two bodies like the sun, and you move them around the center of mass of the system, then they create ripples in space-time. Just like when you move a stick on the surface of a pond, it creates ripples, waves on the surface of the pond, and they propagate out. And so the same way you can have gravitational waves. And Einstein immediately recognized that a few months after he wrote down his equations in November 1915. That was more than a century ago. And then he thought that gravitational waves may exist. And it took a century to detect them. In 2015, almost exactly a century after he formulated his theory of general relativity, those waves were detected from the edge of the universe. And they originated, the signal came from two black holes moving around and merging. And a black hole is another consequence of Einstein's theory that was recognized by uh, Carl Schwarzschild. He was a famous astronomer, the head of the Potsdam Observatory in Germany. And it was, 1915 was around the time when the First World War started, and he was a patriot, Schwarzschild, so he went to the front against Russia, and then over there he realized the solution to Einstein's equations, that in fact, if you put a point mass, you can get a structure of space and time that is now called a black hole. And he sent his solution to Einstein through a postcard, and it was published, and that's called the Schwarzschild solution for a black hole. So when you concentrate matter enough, you end up with a structure of space and time that is the ultimate prison. You can enter it, but you cannot leave it. You cannot exit from it. And even light cannot escape from it. And that's quite remarkable, because it's empty space-time, except there is a mass concentrated at the center of this structure. And by now we know that such objects exist in the universe. I mean, Einstein doubted that they exist back in 1935. He thought maybe they don't exist. But then now we know that such black holes do exist. And in fact, their discovery, the proof that they exist, won 2 Nobel Prizes, one through the gravitational wave method that I mentioned, and the second one is a direct observation of the motion of stars near the center of the Milky Way galaxy, which indicate that there is a black hole of 4 million solar masses, 4 million times the mass of the sun, near the center of the Milky Way. We know that from the motion of stars. By now, we actually even have an image of 2 black holes. And those images were obtained at the Black Hole Initiative that I served as the founding director of at Harvard University.
I was actually very amazed by those images, very intrigued, because I've loved black holes since I was a little kid. And so I really, really enjoy the Black Hole Initiative, the entire thing. So I was very excited to meet you. Talking about black holes have always fascinated scientists for like close to a century now, and all thanks to the groundbreaking predictions of relativity. Could you walk us through the pivotal moments that made black holes a serious consideration in the scientific community, and how our understanding of them has evolved since, with modern research pushing us into some very mind-bending possibilities with the Black Hole Initiative as well?
Right. So the discovery of black holes in the universe was pioneered by Martin Schmidt. He discovered what is now called quasars. These are objects that look like stars, quasi-stars. They are point-like in the images, and then they appear to be great distances. He saw some spectral lines of hydrogen, for example, that are shifted to the red. And that was the first detection of redshift. And these quasars, and that is just due to the expansion of the universe. So these objects are seen all the way to the edge of the universe. And by now, I mean, shortly after his discovery, these very compact sources of light were interpreted as supermassive black holes that have masses up to tens of billion times the mass of the sun. And by now, they are recognized to be at the centers of galaxies. So what happened is, when you make a galaxy like the Milky Way, that's an object that has 1 trillion times the mass of the sun. Some of the gas collects near the center, and as a result of that, it leads to the formation of a black hole. And the main obstacle for doing that is the rotation, the spin of the gas. It just like water going down the faucet, the water spirals in. And so the gas near the center of a galaxy is losing its rotation as a result of viscosity, the similar process to what happens for water in a sink when it goes down the drain. And so that makes a black hole in the center of almost every galaxy that we see. And usually, the black hole contains about a fraction of a percent of the total mass in stars of the galaxy, except that now we see these black holes forming at very early times. less than a billion years after the Big Bang. The Webb telescope saw evidence for some black holes that are about half a billion years after the Big Bang. And they seem to be very massive. In fact, more massive relative to the stars than we see in nearby galaxies. So that's one of the puzzles. How come these black holes grow to be so big, up to a billion times the mass of the sun so early, and they make up a big fraction of the total mass budget? And it's sort of like finding giant babies in a delivery room. When the universe was so young, it turns out that black holes formed very quickly, and in fact, they grew in a way that suppressed the formation of stars around them. So that's why they make a significant fraction of the total mass early on. There are lots of questions about how they did it, but these are the type of black holes you find at the centers of galaxies. Then there is another type of black holes. These are the ones made out of the collapse of the core of stars. So massive stars, when they consume their nuclear fuel, you should think of stars just as nuclear reactors, fusion reactors that are held together by gravity. So you have, a star is just a ball of hot gas held together by gravity, and it burns hydrogen mostly at the core. And if the star is very massive, once the nuclear fuel is exhausted, the core of the star collapses. And if it has enough mass, the gravity is so strong that it makes a black hole. And these black holes are between 3 times the mass of the sun up to 100 times the mass of the sun. The Gravitational Wave Observatory, LIGO, detected black holes throughout the entire range, all the way up to close to 100 times the mass of the sun. And those are much less massive than the billions of solar mass black holes that we find at the centers of galaxies. And of course, the big black holes could have been seeded. They could have started as a stellar mass black hole that started accreting mass and from the environment at the center of a galaxy. So it was sort of like a seed that grew to become the big black holes. And then there is another type of black holes that may exist. We don't know if they exist. And those are tiny black holes, mini black holes, with a mass similar to that of an asteroid. And the reason those are interesting is because they can make up most of the matter in the universe. Most of the matter, 85%, is of a substance that we haven't discovered. We don't know what it's made of. It's called dark matter, and it's different from the ordinary matter that we are made of. We make just 15% of the matter in the universe, the type of matter that we are made of. And in fact, in addition to the matter, there is also dark energy, which makes up even more of the cosmic mass budget. But out of matter, most of the matter, 85%, is of unknown nature. And one possibility is that these were black holes, tiny mini black holes that were made shortly after the Big Bang, early on in the universe. And we don't know if that's the case. But recently, I wrote some interesting papers about these black holes. If they have the kind of masses that asteroids have, asteroids of size a kilometer to maybe 100 kilometers, those black holes have very small size. The region from where you cannot escape. In the case of a black hole that is 3 times the mass of the sun, that region is roughly the size of a big city. It's about 10 kilometers or so. However, if you deal with a billion times the mass of the sun, it's a billion times bigger. It's roughly the size of the solar system. The planetary system around the sun. And if it's a mini black hole with a mass of an asteroid, we are dealing with a size that is between the size of a proton, just a single proton, and a size of an atom. And so recently, I just published a few days ago a paper in the Astrophysical Journal Letters that says, well, if it's that small, you cannot imagine it accreting mass the same way that the big black holes accrete mass. The big black holes have a big mouth, and anything that falls into it is swallowed. But you cannot put in a prison, you cannot put a prisoner who is plump, that whose body size is bigger than the size of the prison. So if you want to squeeze an atom into a mini black hole, it will be difficult because the atom is bigger than the size of that black hole. And so I wrote a paper just published this week that explains how to calculate the accretion of matter by these mini black holes, which is a fascinating topic.
Absolutely fascinating. And also, thank you for the horrifying imagery of giant babies.
It's so continuing the discussion of black holes, as you mentioned, there are different types of black holes, be it the tiny primordial ones, the ones born just a few years after Big Bang, or the massive giants, the massive babies in the galaxy. They're all incredible test grounds for the Einstein's theory of relativity. But since, like as we've read, the Einstein's theory of relativity doesn't fully explain what's happening inside a black hole. So, are there any leading theories that the scientists today are exploring to bridge these gaps?
Yeah, so first let me explain why black holes do not grow to consume all of the galaxy around them. What happens is that just think about these giant babies that are being fed. Once they become very big and energetic, they can shove off the food off the table, and that's what they do in galaxies. So if you feed them enough mass, they release so much energy that the food is being expelled from the environment that feeds them. And that is what happens that's why black holes grow to become a small fraction of the total mass of a galaxy, simply because they release energy that prevents additional matter from falling in. And it's a self-regulating process. If they didn't release that much energy, they would continue to grow and become much bigger. And maybe we wouldn't exist at that point. I mean, the Milky Way has a black hole that is 4 million times the mass of the sun. And if there was no feedback, no release of energy that suppresses the growth of the black hole, it would have become much bigger. And at that point, maybe a star like the sun would not have been made, because it would have been affected. I mean, the environment that we live in would have been heavily influenced by the black hole. I should also say that living near a black hole offers great benefits, because time is progressing more slowly. So you can imagine having a beauty salon next to the black hole where you age much more slowly. You can also, if you look forward at some distance from the black hole, you can see light that came from your back. You can see your back image because light goes in a circle around the black hole. Also, black holes are excellent factories for clean energy. You can throw your trash into the black hole and you get in return free energy. In fact, I wrote a paper a couple of months ago where I said that a very advanced technological civilization might want to have a mini black hole circling its planet. Because if you imagine a black hole that has about 100,000 tons in mass, such a black hole, according to Stephen Hawking, would evaporate within 1.5 years. It will just blow up, release all of its mass in radiation. But if you dump your trash onto this black hole at a rate of a few kilograms per second, which is roughly what you get by flushing the toilet. That's how much water comes down the toilet when you flush it. If you were to feed a black hole with a few kilograms per second, this black hole will keep its mass. And what would happen is that all the trash that you throw into it will be converted with 100% efficiency into Hawking radiation. And it's if you put such an engine, such a factory of energy in an orbit around the Earth, a low Earth orbit, it could supply as much energy as the sun does to the surface of the planet. And that could be a very convenient way of not needing a star to fuel the local economy, you can imagine just having such a mini black hole that gives all the energy needs of a civilization. So I suggested just searching for such systems, looking for a planet that has a moon which is shining very brightly.
It is so interesting that you already told us that because we actually had a question we were about to ask you if a civilization can use a black hole as an energy source in our next segment, which will be the sci-fi segment, science versus fiction, where we dive into the fascinating space where reality meets imagination. So, sir, as you know, there are several movies based on space and time. We were wondering if they were based on some truth or if they were completely made up. So you have answered one of our questions, which was great. So we'll ask you the next.
I
Go
should
ahead,
say,
Pan.
I should say, with respect to movies, there was Interstellar that was
Yes,
guided. I mean, the production of that film was guided by Kip Thorne, who won the Nobel Prize for the discovery of gravitational waves with the LIGO experiment. And he actually visited the Black Hole Initiative a couple of weeks ago. I had an opportunity to speak with him. And he, for example, constructed a computer program that calculated what a camera would see if it falls into a giant black hole of the type that I described before, as it crosses the horizon of that black hole. So you can see those images in the film. He claims that he did the calculations. In fact, he has a book talking about the science of the film Interstellar. And he imagines in that movie that there is a planet orbiting that black hole, um, and I would say that that is indeed science fiction, but it's rooted in science. There are lots. I mean, there is part of the film that is about what happens close to the event horizon of the black hole and whether quantum effects have a big influence. And there, I would say that there is a reference to extra dimensions and so forth. All of this is speculation. We don't really. I mean, we don't know what happens inside a black hole. In my view, my favorite is that the material, the matter that falls into a black hole, in my view, may actually collect near the center and form a very dense object that has the maximum density that we can imagine, which is called the Planck density. And if I had to bet, I would say there is probably a dense star, a compact object near the center of a black hole at the maximum density that we can imagine, the Planck density, where quantum effects play an important role in the context of gravity. There is no singularity. There is nothing pathological close to the center. Einstein's theory breaks down near the center because it doesn't have quantum mechanics as part of it. And so the reason we don't know exactly what happens near the centers of black holes is we don't have a reliable predictive theory of quantum gravity. And I should also say that if we had such a theory, I mean, knowing what happens inside a black hole doesn't have any important consequences for us away from the black hole. It only matters for an astronaut that wants to get all the way in. But there is another singularity, which is the Big Bang singularity. If we go back in time, since the universe is expanding, when we go back in time, there was a point in time when the density of matter and radiation was infinite, and it's called the Big Bang. And that's a singularity in time. And the question is, what happened before the Big Bang? That's a fascinating question because our cosmic roots started in the Big Bang, and if we understand what happened before, we can. It's sort of like figuring out. I mean, if you're born at a particular date, but you want to know who your parents are. I mean, it's very important part of the story. Who gave birth to you? And so the question is, who gave birth to the universe, and why did it all start? And of course, for that, you need also a theory of quantum gravity. And again, I have an idea that I like, which is, once we have a theory of quantum gravity, we could understand what were the conditions that led to the Big Bang. and then we would have a recipe. It's just like a recipe for a cake. If you know what you need, what are the conditions to make a cake, what do you need to do, you can make a cake. And so at the point where we would have a quantum gravity understanding of the initial condition or the conditions that led to the Big Bang, we could try to recreate those conditions in the laboratory. And that is very significant because we might be able to create, at least in principle, a baby universe. And if you were to ask in all the traditional religions, what is the job definition of God? The one requirement, if you want to apply for the job of God, one requirement is that you should be able to create a
Create.
universe. And once we understand quantum gravity, we could potentially apply to that job.
This was actually present in a series, an animated series called Rick and Morty. They created a mini universe to power their engine, and that went on, like that mini universe created another mini universe, a microverse, to
Yeah.
power their world.
So it's possible, it's possible that it's just like babies maturing to become adults and then having babies. And so it's babies all the way. It obviously raises the question, just like the chicken and the egg, what came first, the chicken or the egg? We know that the Earth existed only for 4.6 billion years. So you couldn't have I mean, there was no chicken or egg at the beginning on Earth. It was very hot, and then it cooled and started to, life as we know it started with microbes. So the answer to the question of what came first, the chicken or the egg, is none of the above. It was something different. It was something different. It started with microbes and then multi-cell organisms after a long, billions of years. And then eventually systems, biological organisms got so complex that you started having things like chicken and egg and so forth. And so the same may have happened in our universe, but maybe more recently it was all about baby universes created by quantum gravity scientists, and and that would be also the future. If we manage to understand quantum gravity, we would be able to create baby universes.
But is that something we can do? Can we like have the mini universe create energy for us? Can that be a battery
Oh,
for our car?
well, the point to keep in mind is our universe, if you just take a small portion of it, it has zero energy, in the sense that, especially if you are speaking about early on, when the universe was dominated by matter, or even before that by radiation, the expansion energy, the kinetic energy of expansion, was exactly balanced by the gravitational potential energy. If you take a small portion of the universe, there was the same amount of energy, positive energy in expansion, in kinetic energy, as there was negative energy in the gravitational binding of the matter or the radiation within that volume. So that means you need zero energy. So you don't need any energy to make the initial conditions of the universe, but there may be an obstacle, that there may be, um, you need to overcome some barrier in order to make a universe out of the vacuum. And very often, if you just do order of magnitude estimates, this barrier has a very high energy. We're talking about the ground unification scale, which is 10 to the 15 times, a quadrillion times the mass of the proton. That's the kind of energy that people have in mind for maybe creating a baby universe. Or even the Planck energy, which is even 1,000 times bigger than that, or actually 10,000 times bigger than that. So it's very difficult to reach that energy. In fact, I write essays every day or two on medium.com. You can find them at Avi Loeb at medium.com. That they have a free subscription. And in one of the recent essays, I discussed what are the requirements to reach the Planck energy with a collider. If you wanted to collide particles, just like the Large Hadron Collider at CERN, how big should the collider be? in order to get events at the Planck energy, because that's what you need if you wanted to, for example, create a baby universe. And turns out that using the current technology that we have, it would require, 100 light years, a very large collider. We would need to go through the backyard of other stars. This would be not an international collaboration like CERN is, but an interstellar collaboration. We would need to collaborate with other civilizations to make it happen.
Not
Thank
gonna
you,
lie,
sir.
I'm really looking forward to that.
All of us are. Yes, sir. So going back to, as you mentioned, Interstellar, and since we are discussing the shaping of universe, so there was another term mentioned in Interstellar, wormholes. So when we talk about wormholes, especially movies like Interstellars, and it opens up some mind-bending possibilities. So I would like to ask, are these shortcuts through space-time, will they actually be able to reshape the universe's structure, and will they actually allow us to travel vast distances or even time travel? Will that be possible?
Yeah, so in fact, the story starts with Albert Einstein and Nathan Rosen, who was his postdoc at Princeton at the time. In 1935, they wrote a paper that talks about wormholes. They found a solution to the equations of general relativity that Einstein formulated that allows two regions of space to be connected with a throat that could be shorter than the distance between these regions in the standard space-time. And that was called the Einstein-Rosen bridge. And then it was realized that, in fact, such a solution in the context of Einstein's equations is unstable. So this throat, this bridge, pinches off on a time scale that is shorter than the time it takes light to cross it. So it cannot exist long enough for a passenger to go through it. But then after that, there was some additional work, mainly by Kip Thorne and collaborators, that illustrated that maybe if you have an exotic matter that has negative mass, so it produces a repulsive gravity, if you can make such matter that has negative mass so that the gravity is repulsive, you can actually use it to produce a stable wormhole. The only question is, can we find such matter? It turns out that if you have that kind of matter and you have a wormhole, you can actually construct a time machine that would allow you to visit the past, because through the wormhole, through this throat, you can actually synchronize the two exits of the throat, the two regions that are connected. You can synchronize them, but then if you move one of them very fast, then there would be time dilation according to Einstein's theory of special relativity. Or if you put one of these regions in the gravitational potential of a massive object, time would progress more slowly than in the other case. And this way, you can actually make a time machine, because one end of the wormhole will age more slowly than the other end. So that means that the side that ages more faster would represent the future of the side that represents slower time. And so you could visit your past by going through this wormhole. And there is a problem with time machine, because in principle, if you go back in time, you can imagine a scenario where you can prevent your grandparents from getting married or giving birth to you. And then the question is, why do you exist? That will be a logical inconsistency. And Stephen Hawking formulated a conjecture that you cannot make a time machine. It's called the chronology conjecture, and that would make historians happy, because it means that history always is ordered the same way everywhere, and you cannot go back in time. Otherwise, historians will be upset. I mean, if wormholes exist, they offer two things. One, travel faster than light between two regions, and the other one is to create a time machine. The question is, suppose we encounter the wormhole, which one would we prefer to use first? For me personally, I would prefer to go back in time, because then I can go back before the Second World War and kill Adolf Hitler. I mean, 65 members of my father's family were killed in the Holocaust. They were sent to concentration camps. And I can, change that history by going back in time and killing Adolf Hitler. I can do that. Unfortunately, so that would be my first priority, to make the world better by fixing the historical injustice that was made throughout human history. There are lots of things that you can think of fixing by going back in time. And then traveling to another destination, that obviously is very appealing, but you need to know where to go. I mean, there must be a lot of places that are not so interesting. You just don't know until you go there. But if I had to bet, I would say probably wormholes do not exist, because we never met anyone from our future.
Killing Adolf Hitler creates an interesting dilemma because then you will be the villain in the history. You just killed some random baby,
Yeah, well, I might be the villain in the eyes of some people, but
but you will be
deep in,
the hero in your own. So,
yeah, exactly. I would,
That matters most.
65 members of my family will be alive and happy, and that would be worth it as far as I'm concerned. Because, whatever happens to me, I'm just one person, and these are 65 people, so that I would serve a better good. And it's not just 65, it's 6 million Jewish people that were killed in the Holocaust. So, I would save 6 million people. That's quite a number.
Absolutely, sir.
so do you think science fiction has created unrealistic expectations about finding intelligent life, or has it helped prepare us for the possibility?
Well, I think our imagination is limited to the experiences we had on Earth. And when you go on a date, you can, with a human, you can pretty much imagine what you would meet, because that human shares the same DNA as you have. But when you encounter a date from another star, all bets are off. It could be very different than we are. So in all the science fiction films, you do see something that looks, maybe green in color, the color of the skin, but it looks like a human, or a variation on a human, or some kind of animal that we're familiar with. But it could, in my view, it would be very different than that. For example, now we are starting to develop artificial intelligence, and I mean, people call it AI, but AI could also mean alien intelligence, because these machines are made of silicon, not of flesh and blood, the way the human brain is made. So they are very different than our brain. I mean, our brain is consuming 12 watts of, that's like a small light bulb. That's all our brain is using. And it's 20% of the metabolic power that the human body is using. So, our brain could not grow bigger than it is, because it's already using a fifth of the power of the human body. But these artificial intelligence systems that are made of silicon chips, they consume gigawatts of power, and they have less connections than the human brain. So it's a very different beast. When we try to align AI systems with us, it's to me, it sounds like putting lipstick on a pig, trying to make it more beautiful. It's actually, a very different animal than we are. So I call it alien, because, at some point when these machines become as complex as the human brain, when they have the same number of connections, I think they will also show qualities like free will and consciousness that we have, except they would be alien to us, I think. And so they represent a possibility for extraterrestrial aliens, because we might have a visit not by a biological creature. We might have some sophisticated technological probe that has a brain, an artificial brain in the form of AI. And to understand what it's seeking, what is it trying to communicate, we will need to use our own AI systems. Um, about 100 years ago, there was a philosopher at Princeton called Martin Buber, and he talked about three types of interactions: the interaction between a human and an object, the interaction between a human and a human, and then the interaction between a human and God. And of course, at the time, 100 years ago, there were no computers, so he did not envision the existence of AI. And I think in the future, we'll have additional interactions that will be the interaction between a human and an AI system, and the interaction between AI and AI. And uh, who knows where it will go. And so the reason I bring this up is because science fiction was not really familiar with AI technology the way it's now being developed, and it will get better and better very quickly. And so what we meet from outer space may represent technologies that we never imagined. And if I had to guess, I would say we would probably find some technological gadget before we meet any biological creature that is intelligent.
So
Sir,
I
it's okay, Akhil,
continue.
go ahead.
Okay, so I personally believe it's very arrogant of us to believe that no other life exists in the entire universe. But we haven't found any concrete evidence of life. Do you have
Well,
any theories as to why that is?
well, because we haven't searched properly. So the thing is that for 60 years or so, we searched for radio signals, and that is just like waiting for a phone call. Nobody may call you when you're waiting. And Enrico Fermi asked, "Where is everybody?" He was a famous physicist, and that is a question that every lonely person asks. But what you tell a lonely person is that you need to be proactive. You need to look through the windows of your home to look for neighbors, or maybe leave your home and go to dating sites if you want to find someone. And Enrico Fermi didn't build a telescope, he didn't search. So my approach to that, and I'm leading the Galileo project at Harvard University, is to search for technological objects near Earth, because only over the past decade we started discovering the first objects from interstellar space, and two of them looked a bit weird. One was Oumuamua, an object that was the size of a football field. The first one discovered in 2017, and it was most likely flat, and it was pushed away from the sun by some mysterious force without showing any cometary evaporation. And to me, it was really weird compared to the rocks that we are familiar with. It had a very extreme shape. We don't know what it is. We didn't collect enough data, but next year there will be a new observatory in Chile called the Rubin Observatory that could potentially find an Oumuamua-like object every few months. And then we can look for technological debris, space trash among the rocks that we find from outside the solar system. And we can easily identify objects that come from outside the solar system because they move very fast. They're unbound by gravity to the sun. And just by their velocity relative to the sun, we can tell that they originated from outside the solar system.
Sir, as Akhil also mentioned, it would be very arrogant for us to think that we are the only
Oh, yeah.
people. And as you have mentioned in many of your interviews and talks, that if you read the newspaper every day, we'll realize that we are not the smartest cookies. So, what would it mean for science, for the society, and for the human understanding if we actually confirm the existence of some smarter cookies or the extraterrestrial technology?
Yeah, so I actually, a couple of days ago, I had a meeting. I was invited to speak to a group of spiritual leaders at the Harvard Law School. And they were all religious. And many religions believe in the idea of the Messiah, that there would be some messenger that arrives to Earth and will bring peace and prosperity. And of course, if you look right now, there are at least two wars going around and we are wasting huge amounts of resources on conflicts. And there is a lot of polarization in many societies where people hate each other and put all their time and energy into tribalism, fighting other tribes. And in my view, this problem that we have with politics right now will not be solved by all of us listening to the words of John Lennon, who said, "Imagine all the people living in peace." That's not a realistic solution. I think humanity needs shock therapy. And in my view, the messenger will come from another star once we realize that there is a better way to behave, because there is another civilization that did much better than we did. They arrived at our doorstep before we arrived at their doorstep. And once we find evidence for that, I think it will change the future of humanity in a better direction. And we will all realize that we are all on the same boat, sailing through space, and we better cooperate with each other. And that's really my hope when I study this subject scientifically.
That's a very, very fascinating theory, honestly. Sadly, we have to wrap up the sci-fi segment. I want to thank you, sir, for sharing your captivating insights and perspectives with us. Now, let's keep the momentum going with some more questions as we dive deeper into the intriguing mysteries of the universe.
So, sir, you mentioned Hawking radiation before. So, I've always wanted to ask if you related to the information paradox. So, you already
Yeah.
mentioned what happens to the information, but what once it enters the black hole? But what kind of challenges does this present for our current theories?
Yeah, so the story is interesting, and Kip Thorne mentioned during his visit to the Black Hole Initiative that it was actually a Russian astrophysicist named Yakov Zeldovich who first worked with his students and postdocs on quantum effects around black holes. And when Kip Thorne went to visit Moscow, he took together with him Stephen Hawking, and that was around 1970 or so. And Zeldovich mentioned to him in a conversation with one of his students, Sergei Starobinsky, he mentioned that in principle, quantum fluctuations of the vacuum could be important around black holes. And at the time, Zeldovich was working on one effect, which is when a black hole is spinning, it actually could emit radiation that comes from the spin of the black hole due to vacuum fluctuations around it. And that idea was absorbed by Stephen Hawking. And at around the same time, there was a young student at Princeton of John Willard named Jacob Bekenstein, who noticed that one of Hawking's results, which had to do with when black holes merge, their area grows. He realized, well, maybe black holes have entropy, because we know that entropy always grows in statistical physics. And so Hawking said, oh, that's nonsense. I will try to show that Bekenstein is wrong. And then in the process of introducing vacuum fluctuations to the formalism, he realized that, in fact, Bekenstein was correct, that black holes have a temperature because they emit radiation, even if they are not spinning. And the way to think of that is that if you imagine photons or particles of light that have a wavelength comparable to the size of the black hole, you cannot really imprison them inside the black hole. They already have one of their feet outside the black hole, so they can escape. And so black holes emit radiation with wavelengths longer than the size of the event horizon. And as a result, you have a characteristic temperature, and that's called Hawking radiation. He demonstrated that the vacuum fluctuations near the black hole are very different from ones far away, and that results in the emission of radiation. Basically, the vacuum translates to a heat bath that radiates relative to infinity. And so because there is energy emitted from the vicinity of a black hole, that energy is taken away from the mass of the black hole. So as the mass of the black hole goes down by emitting this energy, eventually the black hole evaporates. And the evaporation is quicker, faster when the black hole mass is smaller. So it's like an explosive process. And then, of course, the question was whether we see any evidence for such evaporation in the real universe. It turns out that only black holes with a mass less than an asteroid of about a kilometer size would evaporate during the age of the universe. And people searched for that radiation from those evaporations, didn't find it. But it's still possible that the dark matter is made of black holes that are more massive than that because they survive. Now, the information paradox is a result of Hawking's result, and that comes because the radiation emitted by the black hole, it doesn't carry any additional information relative except for the temperature of the black hole. It's thermal radiation. According to Hawking's calculation, it's pure thermal radiation. There is no information in it except for the temperature of the black hole. And that is posing a paradox, because if you imagine making the black hole by throwing an encyclopedia book into it, where is the information that was contained in the encyclopedia? Now, you may say the same thing about the sun. Suppose I throw this book into the sun. Well, the truth is that there is radiation emitted by the sun, but it will not be perfect black body. It will not be just thermal. You would be able to recover the information from slight deviations of that radiation. But in the case of the black hole, the derivation of Hawking was giving just perfect thermal radiation. So that became a paradox. So where is the information going? Because if the black hole evaporates, eventually you are left with nothing other than that radiation. So there are all kinds of suggestions for solving this problem, but it's one of the big problems that if we had a theory of quantum gravity, we would know the answer. Most physicists believe that Hawking's derivation is missing something, that in fact the information is encoded, because according to quantum mechanics, information cannot be destroyed.
So, what are your thoughts upon white holes?
Oh, so white holes are just the reversal, the time reversal of a black hole. So instead of matter falling in to a center and then making a black hole, you just imagine the opposite as a function of time. So matter coming out of a singularity, and you basically see it as a source of energy out of nothing. It's not as if you're feeding it, it's just that energy comes out from it. And there was a suggestion early on when quasars were discovered, those objects that are very bright at the centers of galaxies. There was a suggestion maybe it's a white hole, but now we understand that they shine at the kind of luminosity that we expect from the material falling into them, and we see evidence for that. So we haven't seen evidence for a white hole, and actually white holes pose a big problem because in the case of a black hole, we don't understand what happens close to the singularity because Einstein's theory breaks down. The curvature of space-time is diverging there. However, we don't really care. Why? Because this region is surrounded by an event horizon, and no information can escape from what happens inside the event horizon. It's sort of like Las Vegas. What happens in Vegas stays in Vegas. So a black hole, whatever happens inside the horizon stays there. And therefore, you don't care if you live outside the horizon, you don't care what really happens near the singularity. However, if you have a white hole, that's not the case. So in the center of a white hole, there is a singularity, and it affects the entire universe. So the fact that we don't understand what happens in that singularity means that we don't understand what happens in the rest of the universe. You can't say, oh, what happens there doesn't, it affects everything around it, and therefore we won't be able to predict what happens in the universe if we don't understand what happens near the center of a white hole. And that is a very problematic situation. So gladly, we don't have a white hole, we just have black holes, and therefore we feel protected from from not knowing what happens near the singularity.
It has been great talking to you, sir. As we conclude this enlightening discussion, what final message would you like to share with our listeners at the Roundtable podcast and the aspiring scientists of this generation?
Yeah, my message is really simple. You are currently young, and just stay young and never pretend to be the adults in the room. That's the worst that can happen to you, because the adults in the room, they often pretend to know more than they actually know, and they don't admit their mistakes. And one privilege that a kid has is that a kid is not supposed to know everything. And I can say that I enjoy being in that spirit. I remain a curious farm boy the way I was at a young age. I haven't changed much, and it's a great privilege because science should be driven by curiosity. That's what makes it fun. There are lots of old people who are attached to their ego, to prizes, awards, recognition, stature, prestige. Those are people that will pretend that they know more than they actually know. Those are the adults in the room. Never become one of them. Always stay curious, willing to make mistakes, take risks, because that's the fun of life. That you learn something new in the process.
That's great. And as people who have recently turned adults, we can say that adulting is not that great, honestly.
I think we can make together. We can make the world better than it was in the past. So let's forget about the mistakes of. A lot of young people are making a mistake of complaining about the past. Instead of complaining about the past, let's just make it's up to us. Let's make the world better, and forget about the mistakes of the past. Forget about the adults in the room. Just try to change the world to a better place.
Thank you, sir. We genuinely hope that this vision comes true. And we are profoundly grateful for the time and insights you have shared with us today. It has truly been an honor to engage with you on such interesting topics such as the black holes, gravitational waves, and the profound mysteries of the cosmos. To our listeners, thank you for joining us on this incredible journey. As we wrap up, remember that every question we explore leads to new horizons of understanding. Thank you